Hey, what's going on YouTube? We should be live any second now, and I just want to confirm that before we go too much further. Because streaming is hard, man. Like, streaming is so hard. Today, we are going to try multi-streaming for the first time. Today, we're going to try multi-streaming to Twitch. So, I'm also live on Twitch at the same time. Oh my gosh, goodness gracious. Today, we are resetting our freaking series on Fraleigh and Beauregard, Linear Algebra. Today is going to be a fun day. We are resetting, and so the way I'm working through this book is like in a breadth first way. I'm working like problems from the first chapter, then another stream is the second chapter, then the third chapter. Yesterday we got to chapter 9 for the first time. And so today we're resetting and we're going to do chapter 1. This time I want to try to solve 2 problems from every section. So this way, maybe we can get through some of these less interesting problems and get to some more interesting problems sooner. So I'm excited about that. I hope you all are. So let's freaking go. This book is getting beat up. Look at this book. Look at that. Look. Oh my gosh, I love it. I love it whenever like I beat up a book so much. Anyways, so that's pretty. I think it's pretty exciting. Okay. So vectors in Euclidean spaces. So section 1, we're going to solve these problems to begin. Computing just a linear combination of 3 vectors. And then we've got the norm and the dot product. Following that, we will be doing matrices and their algebra, computing the multiplication of 2 matrices. And yeah, of 2 separate matrices, and then finding a squared. And then I haven't written these out, but we will work some problems as time allows. Definitely 1.4, 1.5, and 1.6. And then maybe we'll do a problem from these optional sections. They're technically optional, so not a big deal, I feel, if we don't get to those. I want to solve 2 problems from every section, though, as I said today, so that we can, get to some more interesting material, more interesting, more difficult problems next time. All right, so let's get started. Oh, and y'all, get excited because there's only 10 chapters in this book. There's 10 chapters in this book. So, I've decided for sure next time that we cycle through and we complete this cycle, we're going to add calculus. And then once we get through the whole section again, so I'm going to add 1 chapter of calculus at the beginning of every cycle. Then we'll do 10 streams of linear algebra. Then I'm going to add 1 chapter of representation theory. So then our cycles will be 12 long. We reset and we add 1 on both ends. Our cycles are 14 streams long and then 16 streams. So we're adding calculus at the beginning, representation theory at the end. Representation theory is like more of a graduate level topic, and its application of linear algebra to more abstract styles of math, more abstract graduate level math. So get hyped. I'm hyped. I'm very excited about this. So let's hang out with y'all in the chat. What's up, everybody? I hope you're having a great day. Nobody in the chat yet. Let's go. But I haven't popped out Twitch, so I got to make sure. Everything gets a little harder if I'm multi-streaming, so I got to we got 1 viewer already in Twitch. Look at that. That might be some kind of bot or something, but all right, let's go. So, problem 1, vectors in Euclidean space. We have 4u minus 2v plus 4w is 4 times u. Let's copy these. Let's just freaking duplicate that over here, dude. Okay. Let's erase some stuff we don't need. Okay, so we've got 4u minus 2 times v plus 4 times w. And then while I'm at it, let's also start the next problem, which is minus u plus 5v plus 3w would be negative 1 times u um, 5v and 3w. So it's the same kind of basic structure for both of these problems. It's just that we're multiplying by different scalars when we're doing this linear combination. So 4 times that is 4, 8, 4, 0. 2 times that thing, that matrix, not matrix, vector. It's a 4-dimensional vector. So a vector you can think of as just a list of numbers. So I'm actually going to distribute the negative. So negative 2 times negative 2 is positive 4. Negative 2 times 0, negative 2 times 1, and negative 2 times 6. Okay. And 4 times the third vector is 12, negative 20, 1. Wait. What am 4, negative 20, 4, and negative 8. Okay. So let's give ourselves a little bit more space. Now, this is 4 plus 4 plus 12 is 20. I added the first component of every vector. 8 plus 0 plus negative 20 is negative 12. 4 plus negative 2 is 2. 2 plus 4 is 6. Minus 12 minus 8 is negative 20. So this is our first, this is part A. And then part B, let's see if we can try to get this a little more, can we do this more inline, just like in one step? Yo, sup, I'm done till orthogonal matrix in high school. Really? You've gotten to orthogonal matrices in high school? Dude, that's awesome. I'm streaming, what's up, by the way, AddixU7 in YouTube. How's it going, dude? Have you seen my videos on orthogonal matrices? JEE. Yeah, y'all are hardcore in India, dude. Like, 99% of my viewers on YouTube are all from India, and you all are studying for the JEE, and dude, that exam sounds so hard. That exam sounds so hard. Yo, and what's up, Mainul, how are you? Welcome back to the stream. Okay, so we just reset, dude, Where did I write it? I didn't write it down, but, dude, big announcement. So we reset. We were working. I got to chapter 9, and now we reset. Then we're going to do chapter 1 through 10. We're going to reset, but then we're going to add calculus 1, linear algebra 1 through 10, and then representation theory. So this is a graduate level topic, representation theory. We're going to start adding sections from calculus and representation theory at the beginning and end of all of our cycles. So Gotta work out. We'll catch you later. Take care, man. Leave a comment on the video after it's done if you wanna help me grow, dude. All right, cool. And feel free to drop a comment like with a question that you're working on. Like stump me, you know? Like share a problem in the comment section, and I'll try to work it someday. Who knows? Okay, anyways, let's get back to our nice little Sudoku here. Let's see if we can do these directly in one step. So, -1 minus 10 plus 9. Okay, -1 minus 10 is -11. -11 plus 9 is -2. -2 plus 0. -2 minus 15 is -17. -1 plus 5 is 4. 4 and 3 is 8. Oh wait, 4 and 3 is 7. 0, 30, 24. Okay. Pretty sure that part B is that. So we did it. We did 2 problems this time on section 1. Let's freaking go. Let's get through this book. Now, section 1.2, we have the norm and the dot product. Cool. So I've already written this one out for the sake of an engaging intro of this video, where there's already some stuff that people can see in the first minute before everybody drops off. Yeah, the average view duration, like we're starting to get hella views. We're starting to get hundreds of views. YouTube is showing these streams to people, but people watch for 1 minute and then dip. Some people stick around, but not that many. All right, so let's call these, I mean, these are 2 separate problems in the book, but let's call these parts A and B. Solution. The angle theta between u and 2 vectors u and v is such that the u dot v is equal to the length of u times the length of v times cosine theta. This is an important formula to remember. In particular, if the dot product is 0, then, well, what angle has cosine equals 0? 90 degrees. Because cosine is the x coordinate of a unit circle. Then theta is equal to u dot is equal to the arc cosine of u dot v divided by magnitude u, magnitude v. So for part A, theta equals inverse cosine of u dot v over magnitude u, magnitude v. And in part B, I know I just repeated like the same thing, but there's a reason for that. I just wanted to get part A and part B set up. U and W. in part B, we're calculating the angle between those two vectors. So here, this is our cosine. Well, first, let's leave like some space here, and then let's solve these pieces separately, just to have some space. What is u dot v? U dot v at the top of the page, u dot v is equal to -2 plus 3. You multiply all the coordinates together and then add all of those together. So -1 times -2 is -2 plus 3 minus 4. -2 plus 1 minus 3 in the end. And then similarly, u dot w is u. So we've got 2 minus 1, 11. Let's copy those. Oops. All right, u dot v is -3. U dot w is 11. Let's find magnitude of u. The magnitude of u is the square root of u dot u, which is 1 plus 9 plus, 1 plus 9 plus 16 is 26, square root of 26. And that doesn't simplify, because root 26 is square root of 2 times 3, or 2 times 13. 13 is prime. So that found magnitude of u. Let's get magnitude of v, which is the square root of v dot v, which is the square root of 4, 5, 6. Magnitude of w is this, 4, 5, 14. Oh wait, 4, 5, 14. I wrote 15. 14 was correct. Okay. So let's take that information and move it down here. We need W for this other problem. And we need U and V for this first problem. So, now we have our pieces that we needed. We've got U dot V is -3. Magnitude of u times magnitude of v is square root of, I'm going to see this as 2 times 13 times 2 times 3. So I did prime factorization of those numbers, which is like slightly easier than multiplying 26 by 6, because now I can see that I can factor out a 2. And I have the square root of 13 times 3, which is 39. And that doesn't simplify. And this does not have a special value. So I wonder if I made a mistake somewhere. I don't think so. I think that this is one where they expect us to punch that into a calculator to find an approximate value. But let's just confirm. U dot U is 1, 10, 26. I got that. V dot V is 4, 5, 6. 6. 4, 5, 14. Yeah, we got... In part A, I think that we got the right answer here. And yeah, 3 divided by square root of 39 is not one of these special values that we memorize on the unit circle. So, we can just ask ChatGPT or a calculator. Does arc, can I type? Oh, it does work. Okay, so arc cosine of 0.5. This is 1.04. Why is that? Okay. 1.04 radians is... Wait, if I divide by pi? Yeah, 0.3. Okay. So this is pi over 3. Cosine of 1/2. Yeah, it's pi over 3. That's right. Okay. So the calculator thing in Mac is working. Then arc cosine of -3 divided by 2 square root of 39 did not work. 2 times square root of 39? Okay. And then divided by pi, we have about 0.57, about 5.8 pi, or about 1.81 radians. I forget how do we get that in degrees? So 2 pi radians equals 360 degrees, right? So if I want to convert to degrees and I have radians, I multiply by 360 divided by 2 pi, or in other words, multiply by pi divided by 180. Did I get that backwards? I have 0.03 degrees. That's fairly small. That doesn't seem right. Did I get that backwards? Yeah, times 180 divided by pi makes more sense. Yeah, it should be 180 divided by pi. Yeah, I was just like, pretty sure that's backwards. And that makes sense, yeah, because I would have to multiply by the unit that I want to keep and then divide by the other. See, dude, I'm telling you, once you get used to to complex math, this sort of stuff gets rusty. This sort of stuff gets rusty. Thank you for helping me, Levi in YouTube and Zenithine in Twitch. What's up, y'all? Welcome to my practice stream, everybody. Yeah, I'm done. So this is approximately 104 degrees. Let's see if that's what the back of the book has, if there is an answer in the back of the book. This one was a little trickier. I mean, I guess I could ask ChatGPT. Something feels off that it's not like a special value, but I think I got it. Okay. Cool. That's part 1. Now part 2, we found the dot product. So we're going to find inverse cosine of 11 divided by lengths multiplied length of u, again, is square root of 26. So then, if I do length of u times length of w, I see this as length of u is 2 times 13, length of w is 2 times 7, so this is 2 times square root of 13 times 7, which is 91. Again, we don't have like a special value for that. So this is the exact answer. This is approximately equal to yeah, sometimes you just forget some of the basics, you know? That's okay. Arc cosine of 11 divided by 2 times square root of 91. This is approximately 54.8. Let's use 3 significant digits. Approximately 54.8 degrees. Let's see if so this one is an odd problem, so we can check the back of the book on this one. We could just ask ChatGPT, and it'll solve all of our math homework for us, which sucks if you're cheating, but if you're a self-studier, yo, that's kind of great. Alright, so we are doing number 13. What did I do? Okay. Well, they didn't simplify. Yo, back of the book didn't simplify their radical, bro. They had arc cosine of 11 over root 364. Look at that. Amateur hour. 364 simplifies as 2 root 91. Hell yeah. Okay, we got it. 54.8. Good morning. Hey, Miss You. What's up? On Twitch. How's it going? So I'm going to start multi-streaming again. I think it's worth it. You probably don't know, Miss You on Twitch, that I am streaming mathematics, but now you do. I have a math channel on YouTube. I have 2 channels on YouTube. YouTube.com/@JC Practices Math. If you're watching this right now and enjoying this, that's probably the one you want. But then I also have a guitar channel, which is just JC Practices. So, follow me there, y'all, if you want to catch the VODs and things like that. And my thought is that on Twitch, I am just going to stream both of them. On Twitch, who cares, YOLO. we're going to do both math and guitar and gaming every now and then, but rarely. So Twitch gets the multi-dimensional John. YouTube gets the individual Johns, if that makes sense. All right, so reading cat butt. Yeah, we get a lot of cat butt on this channel. All right, on YouTube. So true. Once you enter higher maths, simple things become rusty. It's true. It's true. Just like arithmetic starts to get rusty. It's like, oh, dude, why am I looking at a number? I'm used to looking at Greek letters. Recently, I was not able to do simple division. I knew something is off, but couldn't figure out what. Lol. Yeah. He agreed, John. Who agreed? What's up, Gideon? Good to see you, dude. Bro, my Newell, you got a 98 percentile on the JEE. Dude, that's actually a huge achievement. Bro, congratulations. That's huge. Anyways, we did it. Thank you for watching that. Today we are solving 2 problems from every chapter 1 section. So 1.3, let's get some matrices and their algebra. 1.3, I already wrote this one out. So, but yeah, we will be streaming classical guitar later, Miss You. I know that you're interested in the guitar content. So I don't know if that's going to work well, just like one account with multiple stuff on Twitch. I have no idea. I don't think it would work on YouTube to have one account with multiple stuff. 98.6, oh, to be precise. I'm here to make sure your hands are in good shape. They kind of are. Yeah, thank you for checking. I haven't been using the keyboard in a while, but it's because I haven't been coding as much. Nowadays, I've been playing guitar and writing math. And I don't know. Yeah, I'm not doing as much typing on the keyboard, but I do like that keyboard. I haven't used it in a while. Someday I should get back to typing and actually making money as somebody who types on a computer. But for now, I'm still, I'm doing math and I'm doing guitar. Yeah. But I don't know, with guitar, I feel nervous about complications at some point. All right, so 5D times 4B. Well, I want to simplify this by factoring out those scalars, and we can use this property of matrices that this will be 20 dB. That's going to be easier than multiplying all the entries in the matrices by 4 and then 5 and doing a bunch of matrix calculations. This is going to be so much simpler. All right, so D times B, let's write them out. -4, 2, 3, 5, -1, -3 is D, and then B is 4, 1, -2, 5, -1, 3. To do matrix calculations, we do dot products of rows and columns. So for example, let me just highlight this. -4 times 4 plus 2 times 5 is -16 plus 10. -16 plus 10 is -6. Here, let's move this little calculation over here. -4 times 4 plus 2 times 5. So now we have one example for anybody who hasn't seen matrix multiplication before. Then we have Negative 4 minus 2 is negative 6 as well. Then we have 8 plus 6 is 14. Then we get 12 plus 25 is 37. 3 minus 5 is negative 2. Negative 6 plus 15 is 9. Negative 4 minus 15 is negative 19. Negative 1 plus 3 is 2. And 2 minus 9 is negative 7. Multiplying everything by 20, well, the best way is multiply everything by 2 and then by 10. So negative 120, negative 120, 370. Oh wait, what am I talking about? That's not 370. 280. Okay, 74, so 740, negative 40, 180, negative 38, with a 0 after it, 40, and negative 140. Cool. I feel pretty good that this is the answer to part A. 5D times 4B. So that was part A. Part B asked, what is, I believe, A squared? So A squared is undefined. Really? Wait. Did I write down A wrong? No, that's correct. A squared is undefined as A is a 2 by 3 matrix. The number of columns of the first matrix needs to equal the number of rows of the second matrix. Maybe a better way to say this that I'm realizing for the first time. By the way, everybody, Luna wanted to send you this message on YouTube. Luna sent you that. I say thank you to Luna. We've got a whole bunch of vertical bar lines. Thank you, Luna. Okay, this is one way to think of it. Alternatively, dot product of rows and columns, for a dot product to be defined, requires length of rows of matrix A equals length of columns of the second matrix, whatever it is. So in this case, the length of rows of A does not equal the length of columns of A, so A squared is undefined. And there's some reasoning to try to explain that. Cool, done. We did 2 problems from that section. Cool. Let's keep going. 1.4, solving systems of linear equations. And now this one I have to write out. But I at least copied the header, so let's copy that. So we're solving systems of linear equations, and we are describe solutions of a linear system that can be row reduced to the augmented matrices. So we're going to do 2 problems. 1, 1, 0. And this is like part A. 1, 1, 0, 3, 0. Negative 4. 0, 0, 1, negative 1, 0, 0, 1, negative 1, 0, 0. 0, 0, 0, 0, 1, negative 2, and 0, 0, 0, 0, 0, 0. So this is part A, and then I'll work the next problem. Well, no. Let me write the second one in case anybody wants to pause the video at this point. Oh, and this also says solution with x2 equals 2 and x3 equal 1. So, and it says give particular solution if it exists. Okay, and then the next problem that's similar that we'll do is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 4. So this is an overdetermined system. 0 to negative 5 to 0. And we want to find the solution, if able, with... oh, it doesn't say. It doesn't tell us to. Well, this already told us the exact... I mean, the solution is right there. 0 to negative 5, 2. I mean, I already see that in this problem. Okay, so part B is almost trivial. Like, if you, it just requires you to like realize and think about the definitions, like these definitions, and getting used to these, like, you know, this presentation of a system of equations. Okay, so part A. Let's find a solution here. This corresponds to some solutions. I'm going to leave some space. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So notice that the third equation says x5 equals -2. The second equation says x3 minus x4 equals 0. And the first, I wasn't going to write all this out, but I did anyways. x1 plus x2 plus plus x4 equals -4. Then, I'm trying to get used to seeing these solutions directly from the matrix without writing out the explicit system of equations. But we see that there will be a free variable, like the pivots are in these entries. These are the pivot entries. So then the non-pivot columns are free variables. So we have solutions with free variables x2 and x4. All right, so we know x5 has to be -2. It does not depend on the free variables. x3, and again, yeah, we have free variables x4 and x2. x3 equals x4. x3 equals x4. And x1 equals, let's give ourselves some space here, or erase this maybe. x1 equals -4 minus x2 minus 3x4. Minus 3x4. So this is the set of equations, or the set of solutions to that linear system. And with two free variables, this set is a plane in 5-dimensional space. So we have a plane, like 2 dimensions, a span of 2 dimensions. And then substituting the specific solution that it gave us, x2 equals 2, x3 equal 1. Well, if x2 is 2, and if x3 equals 1, then x4 also equals 1. x5 is already fixed at -2. And then the only one that's slightly tricky is the first component. -4 minus 2 is -6. -6 minus 3 is -9. Cool. We got it. Pretty sure that this is correct. And I see Levi got the same thing. Nice. Good job. Cool. Now, the second part is a point in R5. Our solution is 0, 2, -5, 2. And it's consistent. There's not like an inconsistent line in the last line or anything like that. So yeah, this is already x1 equals 0, x2 equals 2, x3 equals -5, x4 equals 2. Fairly easy. Pretty easy. I'm glad we got through 2 of these so we can get to some harder problems next time. Okay, section 1.5. Yeah. So now we've got section 1.5. Where did it go? Copy. I meant to start a new note for all this, but that's okay. I'll just duplicate. Okay. Section 1.5, the next problem that we have, we're working a problem about inverses of square matrices. Cool. All right, so we got some large matrices. Find a inverse where A is this large matrix 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 5, 0, 0, 0, 0, 4, 0, 0. I like this. I like the structure of this problem. It's like, it's obvious where they're picking the numbers from, and it makes it more clear what the idea is that this problem wants us to learn. Why the world is weird. Hey, what's up? How's it going, dude? I don't know. I mean, that's a great question. Why is the world weird? Good question. Thank you for asking that question. All right, so inverses of this matrix. Well, can we do this? I think that this section wants us to do it. Yeah. I think that this section wants us to solve this in this approach, but there might be something more clever, but it's really not too bad. So we construct this augmented matrix, and we do row reductions until we get inverse on the left and A inverse on the right. So let's just do it. But I can see that there's going to be permutations of rows. I can almost write it out. I'm just going to write I for now. And then if we interchange the first and last rows, then this entry is in the correct spot. So we need to interchange the first and last rows of the identity matrix. So we'd have 0, 2, 3, 4, 5, 6. I'm really running out of space there. Okay. Slow down, John. This is a huge matrix. Let's just do this vertically. Okay. So what I did is I swapped the first and last rows. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I mean, I think I see that it's going to be... I'm pretty sure that I'm going to see A inverse is 1, 2, 3, 4, 5. Yeah, there's a sixth one. 1, 2, 3, 4. 1, 2, 3. 0, 1 fifth, 1, 2, 3, 4, and then 1 6th, 1, 2, 3, 4, 5. So like instead of doing the entire row reductions, I could multiply this, which I believe is the correct inverse. And if it does, if this times A equals I, then this is correct. Or it is the correct. It is the inverse of A, because if there is A inverse of A of a matrix, it is unique. So I could multiply the original matrix by this thing, and I see... Well, I mean, I guess you would need to do a lot of multiplications. I don't know. We could kind of do this in place. But that process would work. But we can interchange the first and last rows. We interchange those. We interchange the second and next to last rows. And we interchange those inner rows. Right? And then that gets our... If we do it in this process, that gets the matrix in this form. And then on the right-hand side, we did those same interchangings. I think I added 1, 2, no, 1, 2, 3, 4, 5, 6. Do I have one too many? Wait. What the? Did I add an extra 0? I did add an extra 0 here. Oops. Yeah, I was like, something went wrong. Okay, there we go. I love you, bro, because you know philosophy too. How do you know that? Did I say that? How do you know that? What's up, JNNIN? Yeah, finding the inverse of a large matrix is very laborious. It's very annoying. But if you understand the theory around what an inverse is, finding this inverse is not so hard. So we do that, and then we divide each row by the number that we need to, and we find A inverse is this. And we're done. Okay, so that was that problem. I feel confident that that's correct. It's kind of a nice problem, I think. I like that. Next, we have determine whether the span of the column vectors of the given matrix is R4. So this is another problem from 1.5. Determine whether the span of the column vectors of the given is R4, where we are investigating 1, 0, 1, -1, 0, -1, -3, 4, 1, 0, -1, 2, -3, 0, 0, -3, 0, 0, -1. Okay. So we could row reduce this and see if it row reduces to the identity matrix. And if it does row reduce to the identity matrix, then all of the columns are linearly independent, and then therefore the span is R4. We don't need to track what the inverse is. So in other words, we compute rank of A, and if rank of A equals 4, then the column space of A is R4. So to compute the rank of A, we take A and we row reduce it to reduced row echelon form, and we ask ourselves, does this equal the identity matrix? So let's take our original matrix A, and first I'm going to subtract the first row from the... first, before we begin, let's just look at it and see if we can find, just from inspection, is there anything obvious? I don't see any clear linear dependencies between these rows, so I believe that it's going to be R4. If I kind of cheated, I could subtract the first row from the third, and I could subtract the first row from the third, and I could subtract 3 times the first row from the last, or I could add 3 times the first row to the last. And then I see that I could subtract the third row from the fourth, and we would get an upper... I can see the right steps to make this an upper triangular matrix. And if it's an upper triangular, then I know that the determinant is the product along the diagonal. And I can see, thinking ahead to those steps, that... Oh, wait a minute, wait. Yeah. Okay, I see that if I subtract... wait. Yeah, if I subtract the first from the third... I don't know, yeah. I see that it can be converted to upper triangular without zeros along the diagonal. But and then the determinant of that upper triangular would be the product along the diagonal. But we haven't learned the determinant yet. in this. We haven't learned the determinant yet in this section. So I do want to do this by computing the rank, because I believe that in this section we've already defined the rank. Is that true? I mean, yeah, we can compute A inverse, but the important thing is A inverse exists if the augmented matrix can be row reduced to I on the left Yeah, I don't have any other tools. So we haven't yet defined rank. And I'm trying to follow this in the path that this book has been teaching. So I'm going to kind of cheat. And so we can compute. Let's see. What's my mathematical argument here? A inverse exists if the reduced row echelon form of the augmented matrix A adjoin with I is equal to inverse on the left and some matrix on the right. Therefore, if the reduced row echelon form of A equals I, then A inverse exists. Because I just don't want to be tracking all of the inverse matrix calculations if I don't need to. Do we have the theorem? I think that the theorem is taught in the next. Oh, okay, yeah. 1.5, we have a theorem. Conditions for A inverse to exist. The following are equivalent. The span of the column vectors of A is Rn. So I can say by theorem 1.12, A is invertible if and only if the column space of A equals Rn. So we do have this theorem. We have 5 equivalent statements of the span of the column vectors of A is Rn and A is invertible. There's 5 facts, and I'm using the first and fifth in this book. So, but I'm trying to be careful of not using terms like rank because the book hasn't taught rank yet. So, and I don't want to use tools, I don't want to use theorems or facts that are taught later in the book if this section is proving it otherwise. So, A is invertible if and only if column of A equals Rn. A is invertible if and only if the reduced row echelon form of A is the inverse matrix, is the identity matrix. I bet that's also in this. Yeah, that's also in this by part 2. A invertible if and only if A is equivalent. Well, if the row space of A let's see. if A is row, they say row equivalent to the identity matrix. And row equivalent is the term that I'm looking for to say that when I'm doing row reductions, I'm row reducing. I'm like rewriting all of those vectors. Yeah, when I'm adding and subtracting rows, then it's preserving the row space. So this is the other fact. A is invertible if and only if A is row equivalent to I, and A being invertible implies that the column space of A is Rn. So now I have the mathematical tools and theorems and scaffolding to be able to justify this process. So that's important to really understand what you're doing. So let's just copy this again. So we're finding the minimized row space. We're finding the row space of A by adding and subtracting rows from each other. So row 3 minus row 1, as I said, 1, 0, minus 2, and 2 minus negative 1. And then we can add 3 times the first row to the last to get 3, 0, 3. Negative 3 plus negative 1 is negative 4. And then we can 1, 0, 1, negative 1, 0, 1, 3, negative 4, 0, 0. Let's triple that one. Let's just do this in 2 steps because I don't know, it's just easier. Like negative 3 times the third row is 6, negative 9, 0, 0, double this last row to get that. 0, 0, 0, negative 8 minus negative 9 is 1. And now we can subtract that row from all the other ones to get zeros along that diagonal. Then we get 6 here, but then we can divide that row by 6, and then we can zero out all the entries above. We already have 1, 0 here and 0, 1 here. So this is the identity matrix. So the row space of A equals the row space of I, which is R4. Boom. Okay. Yo, what's up, Leo Lectures? Yo, dude, Leo, you keep tuning into like my most elementary streams, dude. I think that's okay, but I'm just saying, like, I just got to chapter 9 last night, and it's nice. We started doing complex scalars, vector spaces over the complex numbers, which isn't crazy, but the 2 streams before that are just so nice, like change of basis theorems and orthogonality. And dude, I've committed. On the next reset, we're gonna get to chapter 10. After that, we're gonna start adding calculus at the beginning. And we're going to add frickin' representation theory at the end. So I guess a little more precise would be every loop we're going to be adding calculus chapters and representation theory chapters. Does that make sense? I'm excited, man. I want to get to some harder and easier math. I don't know why we're ranking matrices. I think they're all great. Yeah, we gotta put them in their place. We gotta order these matrices. Which one is the best? Which one is the greatest matrix? Yeah, dude, I want to learn some freaking representation theory. I took an undergrad representation theory course in college in my second semester, and I wasn't quite ready for it, but I got the general idea of it, and I was just like, this is beautiful. This is so nice. And it motivated me throughout the rest of undergrad. Like when I took abstract algebra, I took our intro to proof / intro to abstract algebra in semester 2 and representation theory and groups in semester 2. That was a bit too much to chew, I feel, but I did an okay job at those courses. And then later when I took like my Dummin and Foote graduate level algebra, having seen representation theory was always so motivating. I was like, okay, yeah, we're talking about like symmetries and stuff, and symmetries are beautiful. Yeah, dude, you should definitely know Leo Lectures. Leo is an awesome fellow YouTuber. Dude, shout outs to these freaking streamers here, man. Shout outs to Leo Lectures. He's not a streamer yet, but he will be soon. I see that coming. I see that happening. Also, K-Theory. And yeah, you probably know him from K-Theory. Doesn't K-Theory have a stupid handle? Yeah, he has K-Theory 8604. Like, what kind of handle is that, dude? Shoutouts to Leo. Shoutouts to K-Theory as well. All right, anyway, so we're going to get some more clickbaity or more, search engine optimized, beautiful handle. K-Theory 8604. Yeah. What is that a special number of some kind? Hey, and Twitch. By the way, I'm on Twitch today. We're starting dual streaming on Twitch. Bell and Jazz, good day. Enjoy speaking in numbers. Yeah, man. Yeah. At some point, we'll be speaking in proofs. We'll be speaking in English again at some point. English and a little bit of Greek. Okay, so we did it. We ranked that matrix and found its rank 4. Great matrix. We're done with that problem. I've been going back and forth, Leo, on do I want to, for my harder math that we're going to add, I've been going back and forth on do I want to do graduate algebra with category theory, namely Aloofy? Because I think category theory is a pretty clickbaity topic, too. I mean, I know a lot of programmers with money who want to learn category theory. But then, dude, I don't know. Every couple of years, I keep relearning algebra on its own. I want to see some applied algebra and applied linear algebra. I think representation theory sounds fun to me. Just personally, I feel I'm going to be a little more motivated by representation theory. And I think it'll be cool to show application of linear algebra to this weird abstract kind of math, right? I got an undergrad representation theory book that I'm excited for. Okay, anyways, we're vibing today. We're just chilling and doing Sudokus. These aren't too hard, but for some people, they're the lucky 10,000 who have been learning this stuff, and that's awesome. So if today's your first day learning about inverses and stuff, that's fantastic. Homogeneous systems, subspaces, and bases. Determine whether this thing is a subspace of Rn. What are the symbols that we use? Yeah, the book uses is W a subspace, where W is the set of x1, x2, xn, such that each element is a real number and x2 is 0. I think that this should be subspace for sure. All right, so we need to prove it in Rn, not R2. Yeah, that should definitely be a subspace. But the trick is showing it and clearly stating it. Gonna go record a bit of a video now. Fingers crossed, construction isn't loud. We'll just have to see. Dude, I'm telling you, Leo, do exactly what you're doing. Just stream it instead of recording the videos. I think that you'll get more audience, and it's more fun too. You get to chat with people during it. But I don't know. Maybe not. Like, maybe it ruins the videos if I'm chatting. I don't know. But I think that what you're doing is awesome, and we should have more math streamers out here on the interwebs. It should be a thing. Like, why aren't there as many people streaming math as there are playing video games? Like, let's get just as many. Like, we're sorely behind the video game streamers, and I think that there's a lot more people out there studying math than playing video games, actually. Okay. So we show W is a subspace by verifying or checking closure under vector addition and scalar multiplication. So let x and y be in W, then x plus y is some x1 plus y1, 0 plus 0, x3 plus y3, and xn plus yn. Which is of the form W. I'm just going to go ahead and just say that. I think that's enough. Kx is kx1, k times 0, which is, well, 0. Kx3, kxn, and this is also in the format of W. So we're done. That's it. Closed under vector addition and closed under scalar multiplication. So that's what we needed to see, and now this was one problem, Ooh, okay. And now the next one says F&B 1.6 prove that the line y equals mx is a subspace of R2. There's a hint, but I'm going to skip the hint and try hard mode. And I think I should be able to get this, I hope. Given that I've studied math in the past. So, let x1, y1, and x2, y2 be points on y equals mx. Then x1, y1 is x1, mx1, and x2, y2 is x2, mx2. Let's give these names just so that U and V, why not? U and V, or A and B, or something. Then U plus V is x1 plus x2 m times x1 plus x2. And this does lie on that line. K times any point is kx1, and then k times mx1. And this is also, well, I guess if I'm going to type check this in Lean or something, we got to do this. So we showed closure under vector addition and closure under scalar multiplication. Therefore, the line is a subspace. There's not much audience in maths community. I mean, I think it's just silent. I think most people use social media, dude. Most people do. Even people who study math. I mean, maybe people who study math seriously are not on social media that much. But I don't know, dude. I think that there is a community out there. What do you think? Levi, I mean, you're here, right? And you're enjoying it. Like, even if we're just streaming to, like, motivated high schoolers who have too much free time, you know, like, I think that's still valuable. Okay, we did those two problems. How long have we been streaming today? This book is getting beat up. Do I want to do a Markov chain problem? Or do I want to just call it a day? How long have we been live? An hour and a half, right? Hour and a half, not bad. Kind of want to switch over to guitar. Because these next second... No. Let's do a couple more problems. But I'm just going to do one problem from these optional sections, or maybe two from the Markov chains section. I'm a little more interested personally in Markov chains than binary codes. I'm like way more interested actually in it. 1.7. So we'll do one or two. Application to population distribution. Let t equal 0.3, 0.7, 0.4, 0.4, 0.2, 0.1, 0.3, 0.1, 0.5, 0.3, 0.1, 0.5. Be the transition matrix for a Markov chain. And let P equal 0.3, 0.2, 0.5 be the initial population distribution vector. Question 1. Find the proportion of the state 2 population that is in state 3 after 2 time periods. Find the proportion of the state 2 population that is in state 3 after 2 time periods. Okay, I'm actually a little bit confused by that. State 2 population that is in state 3 after 2 time periods. So I think that what we're finding here is t squared times p but because t squared is 2 time periods. What I'm a little bit confused by is that this is some vector, some new vector, p1 prime, p2 prime, p3 prime, right? So I would think that p2 is the proportion, or is the proportion of population in state 2. So what does it mean for a proportion of state 2 in state 3? Like, is that the number? Do I need to be calculating the difference and like seeing where the proportion is distributing to between state 1, between time 1 and time 2 or something? I think so. I think that's what I'm supposed to do. So I think we do like at time 0. Yeah, let's do at time 0, the initial population is 0.3, 0.2, 0.5. after one time period, we have the matrix 0.3, 0.7, 0.4, 0.4, 0.2, 0.1, 0.3, 0.1, and 0.5 times the initial. And you know what? I don't feel like doing this as mental math. I think that the book definitely wants us to just calculate these with a calculator. 0.3 times 0.3 plus 0.7 times 0.2 plus 0.4 times 0.5. So then this element is 0.43. 0.21 and 0.36. Okay, so just verifying, if we add those numbers together, we get 54, 64, 64 plus 36 is 1, or 100. So that's after one time period. Then after two time periods, this is 0.3 times 0.7 times 0.4, 0.4, 0.2, 0.1, 0.3, 0.1, 0.5 times 0.43, 0.21, 0.36. And we could calculate all of it, but this, and why don't we just do it? But the question is really asking state 2 moving to state 3 after two time periods, I think. So I believe that the question is asking for the proportion of moving from state 2 to state 3 do I need to do this from... Do I need to somehow track this from T0, though? I guess. Yeah, I'm trying to think in terms of Markov chains, and Markov chains are somewhat new to me. This would be after two time periods, but I think I need to be tracing the initial population from state 2. Is there a smarter way to do this? Does this work? All right, so okay, so I think. Oh wait, no. Moving to state 3 would actually not be this, I mean, it's coincidentally also a 0.1, but I think that it's actually this one that it's multiplying by. But that's after one time period. So do I need to track this across? Okay. This is kind of neat. 0.3 times 0.43 plus 0.7 times 0.21 plus 0.4 times 0.36. I just want to write out this just out of curiosity. 0.42 0.4 times 0.43 plus 0.2 times 0.21 plus 0.1 times 0.36 is 0.25. And 0.3 times 0.43 plus 0.1 times 0.21 plus 0.5 times 0.36, 0.33. Okay, so in other words, we have three states. State 1, State 2, and State 3. And we have an initial proportion of 0.3, 0.2, 0.5 initially. And the probability of moving from State 1 to State 2... the probability of things shifting to State 1, if I'm understanding how to mark, and I could check this section, but I think it's better for me to try to come up with this idea so that it'll stick in my brain better. I think that the probability, there's a 0.3 chance of an element staying in State 1. There's a 0.7 chance of moving from State 2 to State 1. Yeah, this makes sense. And there's a 0.4 here, let's do this a little nicer. There's a 0.4 probability of moving from State 3 to State 1, I believe. And then moving to State 2, there's a 0.4 probability from 1 to 2. There's a 0.2 probability from 2 to itself. And there's a 0.1 probability of 3 to 2. And then finally, we have from 1 to 3, we have 0.3. From 2 to 3, we have 0.1. And a 50% chance of staying in State 3. So this is our Markov chain. So if the question is asking from the initial state, what proportion is moved to State 3? then the answer would be the proportion of moving from 2 to 3 after 2 time periods. This is confusing me a lot. Like, I could decompose it as say 2 to 1 to 3 from, because 2 either moves to 1, 2, or 3. And we want these things to land in 3. Right? And the probability of moving from 2 to 1 is 0.7. So I'm claiming that this equals the probability of 2 to 1 times the probability of 1 to 3 plus the probability of 2 to 2 times the probability of 2 to 3 plus the probability of 2 to 3 times the probability of 3 to 3. If that's what the question is asking, then we have 2 to 1 is given by 0.7 times 1 to 3, which is 0.3, plus 2 to 2 is a 20% probability, and then 2 to 3, which would be a 0.1 probability. And then finally, from 2 to 3, and then staying in 3, which is a 0.5. So we've got 0.021 plus 0.02 plus 0.05, which would be 0.096. Is that right? Oh, wait, no, 0.091. So I think 9.1% of the initial... Hey, Leo, how are you? Waiting for you in K-Theory. Yeah, everybody, like, I feel like I'm, like, the opener for K-Theory. I'm, like, the, like, side stage. Yeah, y'all, just go dip out of here and go say hi to K-Theory for me, dude. Say hi for me. What's up, Sheikh Syed Aman? How are you? Good to see you. Thank you for stopping by. Okay. I believe that this is the answer. I think that this is truly the answer. But if this is true, we should see, because the probability of 2 landing in 3 after some set of moves, after any set of transitions, it's not obvious to me that this is already the case. But I think we should see that after 2 time steps, everything in 2 has landed. The probability of landing in 3 plus the probability of landing in 1 plus the probability of landing in 2 should add up to 100%. So I'm kind of curious. Do these work out? We already calculated 2 to 3, so then we need to find 2 to something to 1. 2... I'm going to write this as 2 to x to 1 equals the probability of 2 to 1 to 1 plus 2 to 2 to 1 plus 2 to 3 to 1. And similarly, oh wait, shoot, I already did that one. Yeah, whatever. Erase. Oh wait, no. I knew what I was talking about. This makes sense. I calculated 2 to x to 3. Here's 2 to x to 1. 2 to x to 2 would be 2 to 1 to 2. Shoot. Alright, 2 to 1 to 2, 2 to 2 to 2, and 2 to 3 to 2. And then we already found 2 to x to 3. We already found earlier is 0.091. So this is p of, I'm going to give the subscripts p from 2 to 1 and then multiplied by p 1 to 1, p 2 2 times p 2 1 plus p 2 3 p 3 1. Well, if this is the answer, then we didn't use the initial... We don't need the initial population that the problem gives us. So, something slightly feels off, but... Alright, so similarly, P21, P12... P22, P22, P23, P32. 2 to 1 is 0.7. Do we have any more 2 to 1s? Yes, right there. 2 to 1 is right here. And we already calculated the last one. Okay. Now, P from staying in state 1 is 0.3. Anywhere else where we have 1s? Nope. From 2 to 2 is 20% probability. 2 to 2. What else are we missing? We're missing from 2 to 3, 10%. 2 to 3, it's 10%. And now we're missing 3 to 1, which is 0.4. That sentence is fully substituted. Now, 1 to 2 is 0.4. Three to 2 is 0.1. And then we can, let's see if my idea made any sense to begin with. I think that it should work. I think that this seems to make sense to me. 0.7 times, dude, that's crazy to me. That's like somebody dropped in here and is like, yo, dude, leave this stream and come join me in this other stream. That's a little rude, actually. Like, I'm pretty open to like self-promotion of other people, and like, you know, rising tide lifts all boats and all that. You know, I'm pretty open to shouting out other streamers and things, but it's just like a little step too far to show up and be like, hey everyone, I'm streaming now, or hey everyone, I'm about to stream, come join me. Or for somebody to show up and be like, hey, come join me in this other stream. That's a little far. Like, hey, why are you watching this guy? Come watch this other guy. Okay, I get it, but that's a step too far. There's an etiquette to streaming. So, if my idea works, these should add up to 1. And I think that my idea should work. I don't think that it did. Something seems wrong. Oh no, something went wrong. 0.7 times 0.4 plus 0.2 times 0.2. Okay, either I wrote down a number wrong or something else, because these numbers don't add up. They don't add up to 1. Why wouldn't it work? Because ultimately, a thing that's in state 2 should end up in state 1, 2, or 3. So why didn't this work? I wonder if I copied a number incorrectly into this Markov chain. This is after, not after 2 time periods, but after the second time period or something. That is like, what this line is saying is that the proportion of the population that's in state 2 after the first time period that moves to the third state is 0.021, I think. I don't know. Right now I'm making stuff up. Let's just find out. Let's read the book. Let's read the section. It's good to be finally having to read a little more of this section and try to understand it. So, is there an example that's similar? Transition matrices. Oh, wait. Okay. Wait. T squared is... Okay. Yeah. Because if we have a transition matrix, Tij, the element Tij is the probability of state I to state J. How does the book say that? How does the book write that? Represents the proportion of the population moving from state J to state I. Oh no, okay, so I got this backwards. Is okay. Not the percentage. Okay, wait. I don't know if I fully understand this right now. Tij is the proportion of the population moving from state J to state I. Okay, so I need to remember that it's like kind of backwards in the subscript from what I was thinking. Light bulb. Yeah. What's up, Leroy? How's it going, dude? What's up? Thanks for tuning into my practice stream. Then, after 2 time periods, if we have some initial vector, then it would represent from an initial population So what I'm looking for is, because the problem was asking about moving from 2 to 3. So I'm looking for T32, which would be this entry. Yeah. So I think I understood the correct element of the matrix to analyze, which is, oh, wait. Oh, shoot. I didn't actually square the matrix. So that's a problem here. I should have squared this matrix. Okay. So I was very close on this. So we don't need the initial state vector what we just need to find is t squared. Um, 0.3 times 0.3, where is, okay, 0.3 times 0.3 plus 0.7 times 0.4 plus 0.4 times 0.3. This element is 0.49. 0.3 times 0.7 plus 0.7 times 0.2 plus 0.4 times 0.1. 0.39 in the top middle entry. Now in the top right entry, we have 0.3 times 0.4 plus 0.7 times 0.1 plus 0.4 times 0.5. 0.39. But we don't actually need to be, again, calculating all of these. So that's not very elegant. We don't care about those numbers. What we care about is t squared 3, 2. We care about the third row, second column. So all we have to do is 0.3 times 0.7 plus 0.1 times 0.2 plus 0.5 times 0.1, which is 0.28. This is the proportion moving from state 2 to state 3 after 2 time periods. I feel pretty good. I feel pretty confident now that this is the correct answer. Pretty good, just chilling. Yeah, likewise. So, that's the only number we needed to actually find. Let's see. Is this in the back of the book? Is this an odd problem? It is. Great. So I can... It says, find the proportion of the state 2 population that is in state 3 after 2 time periods. Heck yeah. Section 1.9 is 0.28. I got it. Okay, yeah, I want to understand Markov chains much more than binary codes, so let's do the next problem too. Fraleigh and Beauregard. Uh, 1.7. We are working find it's the same kind of problem. Find the proportion of the state 3 population that is in state 2. It's the same problem, just a different states. After 2 time periods. So let's get a repetition here. Where our matrix T is this. So then t squared, what we're finding is of state 3 that moved to state 2. So we care about the row 2 third column entry, which is the dot product of 0.4, 0.2, 0.1 dot product with either dot product or write it as a matrix multiplication. 0.4, 0.1, 0.5. So dot product of a row and a column. Second row, third column is 0.16 plus 0.02 plus 0.05, and that is 0.23. I think that's right. Yeah. I think that is correct. So t squared, this represents, and now this is a much cleaner, simpler solution than what I was trying to fumble around with earlier. Hey, Adixio. Actually, dude, having a problem in understanding complex number application as vectors and 2D. Any good books or videos for reference? Well, yesterday, actually, just yesterday, I filmed a video with a bunch of problems. So you could find my chapter 9 video on complex scalars. And in this, I worked a few exercises. I could show you some of them because it's still in this notepad. Yesterday in my video, which you could just scrub around in, you can see several problems. These are some of the problems I worked yesterday. I remember I definitely did this one. I don't think I got to this diagonalization problem, but I wrote down some theory. So, yeah, these are the problems that I worked yesterday. And then I took some notes on complex numbers and some notes on complex, vector spaces of vector spaces over complex numbers. So there's like some of the algebra and properties of the conjugation in the complex numbers. And I reviewed for myself a bit about polar coordinates. I did a few examples from the book, which are basically exercises, right? And I found some inverses of matrices using complex numbers, which is a little tedious. Determine whether that set is independent. Yeah, I did some good stuff yesterday. So if you want to watch that, it was my video from yesterday, coincidentally. And we landed on this bit about the Euclidean inner product, which I don't remember. I didn't remember that, but it seems pretty awesome. And this theorem. Cool. All right, so speaking of, I had to stumble and look at the book to understand these two exercises, which I can cross out now at least. Let's work a couple of the examples from the section, because I should be working these examples first before I go to the exercises, because the examples are worked exercises, right? So I should be doing that before going to the exercises. Fraleigh and Beauregard 1.7. The first example I have here is let a population of a country be defined as state 1 is poor. Everybody's either poor, middle income, or rich. I'm using shorthand. So suppose over after a 20-year period, about one generation, of the poor people 19% become rich. Oh wait, no, become middle income. So, poor people, 19% of poor people become middle income, and 1% become rich. So then, of the middle income population, 15% become poor, and 10% become rich. Of the rich population, 5% become poor, and 30% become middle income. And then this thing says, give the transition matrix for this data. My solution here, before I read the section, is going to be recalling that if T is a matrix of Tij entries where Tij represents movement from state J to state I. So that's going to be shorthand. Gotta go now. Have a nice day, mate. Hey, take care, dude. I didn't even know you were here. What's up, Ta3575? Thanks for saying hi, dude. Y'all, if anybody's watching right now, let me know if you enjoy this. Why don't I let you all work this problem? I want to play you all a guitar song. How random is that, right? Here's a guitar. Here's a mathematics stream with some random classical guitar thrown in. You all, this is your chance. I encourage you to please work this problem right now for yourself. Try to play it, or try to work it. If you enjoyed this classical guitar, I hope you subscribe to my secondary channel, JC Practices. YouTube.com/JC Practices. The display name is JC Practices Math. Okay, I'm in drop D. In drop D, let's play the Bach cello prelude. glad that you liked it, Vob. Vob Edits. I'm really happy to hear that you liked it. Thank you. So I'm late today. I mean, I guess. Yeah, you are kind of late, I guess. I've been going for 2.5 hours now because I'm a nerd and I just really enjoy math that much. So, dude, if you enjoyed that, please do subscribe to my guitar channel as well. After we're done... Oh, hey, and Stucky on Twitch. What's up? By the way, Vob, if you prefer Twitch, I'm starting to multi-stream now. I'm doing YouTube and Twitch, and I guess vice versa to you and Stucky. If you prefer YouTube, I'm also on YouTube nowadays. So, if you enjoyed it, please do subscribe to my classical guitar YouTube as well. Thanks, y'all. So that's my classical guitar YouTube. Here's my mathematics channel as well. All right, thanks. Let's work this problem. I was thinking about it a little bit while playing. Really happy that y'all enjoyed that. Cool. So we've got this population of poor, middle income, and rich people, and there are these transitions that the problem is telling us. So the row represents the destination of these transitions. Like Tij is moving from J to I, so the row is the destination, and that's something I realized and like remembered and kind of constructed for myself while working the problem earlier. I was like, the row must be landing in that new state for each of these. So then the column is the initial state. And I got that right. So if somebody is poor, there's a 1% chance that they become rich. And there's a 19% chance that they become middle income. Well, then that means that there must be an 80% chance that they stay poor. That's so sad. Now, middle income people, 10%... Oh, wait. Oh, shoot. I wrote 0.1. I meant 0.01. There's a 1% chance, but I added those numbers correctly. Okay, so middle income people, middle income, 15% become poor, 10% become rich, and then the remainder stay middle income, 75%. Now, rich people, 5% of rich people become poor after one generation, 30% become middle income, and then the remainder, which would be 65%, stay rich. So here is our solution. Let's check. The book, wait, what? Did I write these wrong? Of poor people, 19%, did I do that wrong? Okay, wait. Okay, I wrote something wrong. Poor people, 19% become middle income, 1% become rich. Oh, yeah, I wrote this backwards, didn't I? I still wrote it backwards. Okay, let's do this again. Okay. Whoops, all right, take two. All right, so let's get an example. T11 represents moving from 1 to 1. In this example, I'm moving poor to poor. But a more interesting one is T12 means moving middle income to poor. And T13 is rich to poor. Yeah, so I wrote the transpose of the correct matrix. So, knowing those pieces of data, what's the probability that a poor person stays poor? Would be 0.8. What's the probability that a middle-income person becomes poor? It's 0.15. And then what's the probability of a rich person becoming poor? It's 5%. Okay. And then I want to start being able to see these without having to write them out. So let's try to get rid of that. Now, what does that row 2 first column represent? It means a poor person becoming middle income. Poor person becoming middle income, right? Yeah, poor person becoming middle income. That's correct. 0.19, and then a middle income person staying middle income would be 0.75. And then a rich person becoming middle income is 0.3. Now, in this last one, it's a poor person becoming rich, 0.01. A poor person becoming middle income. Oh, wait, no, sorry. The third row is landing in state 3, right? Yeah, it's been 2.5 hours. Yes, yeah. We're going to wrap up right after this one. I'm going to cross over and stream classical guitar practice right after this. So you can keep hanging out with me if you join the guitar channel. All right, so this next one is middle state landing in second state landing in third state, which is middle becoming rich, 0.1. And then this last entry is rich staying rich, which would be 65%. Okay, now we check 0.8, 0.15, 0.05, 0.19, 0.75, 0.3, 0.01, 0.1, 0.65. We got it. All right, so now that's corrected, and I got a little bit of practice writing out a transition matrix. Yeah, dude. Tell me the guitar channel, and when I go live, I'm going to go live in like a minute. I will raid. I'll raid the channel. And here's the link. So, yeah, dude. I hope to see you there. It's fun. It's a bigger channel. I mean, I've got more people watching me there. And I don't know, music is fun, right? Like, I think most people enjoy classical music to some degree. So, thank you, everybody. It's been a pleasure. Let me set up the new stream so that we can actually do this crossover thing. On Twitch, we're just going to continue streaming here on Twitch. Yeah, so thank you. Thanks for joining. Thanks for hanging out with me. Ba-ba-da, da-ba-da. So today is day 863, practicing classical guitar. And I don't know yet what I'm going to be practicing today. We're going to figure it out as we go. We're going to go as soon as possible. Scheduled. Thank you, everybody. If anybody's watching the VOD, please let me know. I don't think anybody actually watches the whole thing. I think a bunch of people watch 1 minute of these videos. But if anybody watched the whole thing, dude, comment in the comment section. I will give you a shout out. You're an absolute legend if anybody watched the entire thing. I doubt it. you know, I doubt it, but maybe. I have to change my login. Oh, this is very tedious. This is very, very tedious. Your most favorite music, come live. Yeah. I have to set this all up. I am Till from the start and studying with you parallel. Yeah, dude. Yeah, man. It's great. Oh, you've been watching since the beginning of the stream? Like, do you mean the start, like the first, like day one video? Or do you mean from today, like you're studying with me? Either way, that's awesome. I'm very happy that people are enjoying this. Can I not redirect? Why can't I redirect? Okay, I don't know. I haven't figured this out. I don't know why I can't redirect from here. Do I need like 1,000 subscribers or something first? Dude, that's crazy if so. Okay, well, I don't know why I can't redirect, but guitar stream. And yes, I definitely love classical music. I love classical guitar specifically. So thank you. Hope to see you there. Take care, everybody. I hope you're having a great day. Come hang out with me. Come keep studying with me. I might have some math over there too. You know, we get math as background content for the guitar stream, and then guitar as a background content for the math stream. All right. Take care, everybody. Thanks for watching. Bye. Bye. See you there. And I'm going to continue on Twitch. I wonder if this is going to